Okay, everybody, so welcome back. Last time we had computed a few of these line integrals. Um, we're kind of starting to get the hang of at least how to. Someone asking chat, there's only two MATLABs total. Yep, that's right. So only two MATLAB total. So I'll post the other one. I don't know, sometime later today, and it'll be due, like I said in that previous announcement, at end, which means that, we could say that it's due on the last day of class, but as long as you get it in to me, within like a day or two of that, that'd be good. Uh, so anyway, what was I saying? Oh yeah, so we had been computing some line integrals, and maybe we hadn't talked that much about how nasty a line integral could be in general, and we'll get to that shortly. But don't think that just because a line integral is technically a Calc 1 integral, right? Once you have actually plugged in the the vector field, or once you've plugged your parameterization into the vector field and you've dotted it with dr dt, that is technically just one big function of t, and you're integrating that with respect to that single variable t. But that doesn't mean that it's simple to do just because it's a Calc 1 integral, because as you might remember, there's just a lot of integrals that even though they're fairly simple to write out, you just flat out can't do them, right? So even pretty simple expressions you just can't do. So these line integrals can be really, really, really nasty. In fact, we're going to have kind of an idea of exactly how nasty they could be, because we are going to come up with ways of getting around computing them. So we are going to come up with some clever ways that we can compute a line integral in a maybe more convenient way. Okay, what is something conceptually we can say about line integrals? So we had previously talked about the orientation of a curve mattering. So let's consider some curve I have, and I'll just draw something in the plane here. So here's my curve C. This curve has some smooth parameterization, and that parameterization would include an orientation. So let's say that the orientation along this curve C is this one. Okay. Now, I have mentioned previously that when I am computing the line integral of some vector field along a curve C, right, so here's my notation for that. All right, so here's my f.dr thing underneath my integral sign. So when I'm computing this thing, I have said, and I made a big point of pointing this out, that the orientation of the curve matters, right? And this was something that was not true for a line integral of a function along a curve, okay? And that's because for the line integral of a function along a curve, this dr term, I was taking the length, right? So it actually didn't matter. But I'm not doing that for a general line integral. And so the question is, how does orientation matter? Well, to see that, let's take, as far as the points go, let's take the same curve. Okay, meaning that I want to consider the exact same curve, except, so that is, it traces out the exact same trajectory, but associated to this curve that I've outlined is the opposite orientation. Okay. So it's the orientation going in the opposite direction. All right, and so once I've done that, I'm going to call that curve minus C. All right, that makes sense. So we've talked about this previously, the notion of looking at a curve and then looking at the curve with the opposite orientation. The nice thing about a curve is that there's only two choices there, right? So you can be going this direction or you can be going the opposite direction. Okay, so you're either going this way or minus that way. Okay, and so if we take the exact same curve but consider the opposite orientation, that is us looking at the curve what we call minus C. Okay, and so the question then becomes, what is the line integral of some vector field f along a curve where I've taken the opposite orientation. Okay, well, it turns out that this is just minus the regular line integral along C with the positive orientation. Okay, this actually isn't too deep of a fact or anything. In fact, all of you could probably prove this pretty quickly just by writing out the definition of line integral. Let's quickly do it just for fun here. So if I look at this quantity, the line integral of the vector field f over the curve minus c, well, if c has a parameterization that we write as r of t, so this gives us x of t I plus y of t j plus z of t k, then when we compute dr dt, right, that's our usual, so dr dt in that case would be the exact same. It would be dx dt I plus dy dt j plus dz dt k, like it always is. So for minus c, instead of having dr dt here, what do I have instead? Well, I have minus dr dt. So this would be minus dx dt, minus dy dt, minus dz dt. Why? The reason for that is because the orientation for a curve is determined by the direction the tangent vector is pointing. And so for the curve C, if we have parameterization R, when we compute the quantity dr dt, right, this is going to be, here we're not necessarily talking about the tangent vector, that is the unit tangent vector. We're just happy to talk about any tangent vector. And so any tangent vector computed as dr dt in this way is going to point, right, in this direction indicated here. It's going to point like this. And so to take the opposite orientation, I'm just taking minus dr dt everywhere. And so really this is, if you like, you can write this as like the line integral over C of f dot minus dr. Is kind of abusive notation here, but that's exactly what's happening. So what's happening here is this is the integral from, if t lives in window, say, right, a to b, so this is the integral from a to b of my vector field f with x t, y of t, z of t plugged in, and I'm dotting that with minus dr dt that I'm not going to write out again. I'm integrating that dt, and this minus sign pulls out, and that's what gives you. So this is minus that whole integral. I'm not going to rewrite it, but that integral is just literally the definition of the line integral, f dot dr. Okay, so that's why this is. Like I said, this isn't too deep or anything. This is just pretty simple application of the definition of line integral here and orientation on a curve. Okay. So that's one conceptual fact we have about this. And of course, like trivially from this, although you didn't have to talk about this in order to say this, I can have the same force, right, represented by my vector field F. And if I'm thinking of the line integrals computing work, work done by that force on some object as it traverses that path, well, different paths, right, might yield different amounts of work done, even if the force remains the same, right? It could be the same force, but that could do different amounts of work depending on the path. And of course, that's totally, that makes perfect sense to us. But of course, you can see that trivially from this, right? Since in that example we did at the end of the last lecture, where we computed the work done was 2 pi squared by that force. If we just took the exact same path, except instead of making it go upward along the helix, we made it go downward, the work done would be minus 2 pi squared. So clearly different in a trivial way. So I wanted to introduce some notation that we're gonna use. We are going to interchangeably use for line integrals, and this is the following. So if f is written in the usual way, my vector field is mi plus nj plus p k, right? And I have a curve C. It's a smooth curve, and it's parameterized by r of t in the usual way, so I won't rewrite r. Again, whenever I write an r like this, you can assume that this is what I mean. Okay, for t living in some closed interval, a, b. All right, then just the definition of line integral. So this integral over c of f dot dr, this is by definition what I wrote on the previous page, the integral from a to b of my vector field f with this parameterization plugged in the usual way. Dotted with dr dt. Okay, now if we write that out in terms of f, where these m, n, and p's are each functions of three variables, right, then this becomes a pretty long expression. So this would be the integral from a to b of, here I would have the vector m with x of t, y of t, z of t plugged in, right, I, plus n with x of t, y of t, z of t plugged in, times j, plus p with all those plugged in. Okay, so that's my first vector, and I'm dotting that. So this dot continues on to the next line because I don't have enough room to write it. So I'm dotting that by the vector dr dt, which I'll just write as dx dt I plus dy dt j plus dz dt k. All right. Okay, and all of that after I've computed that dot product, that is just some big function of t, and I'm computing the integral from a to b of that thing, okay, with respect to t. But dotting this is easy, right? In fact, this is the integral from a to b of m, and I'm not going to write this whole thing written out again, but it's m times dx dt plus n times dy dt plus p times dz dt. Okay. And so, for that reason, a lot of times we use abbreviated notation for this. Well, you might say, wait, abbreviated, like this is very short, and what I'm about to write is longer than this. It's abbreviated in the sense that you don't have to put the force here, it's already there. So, so what do I mean? So we write this, so for this reason, we have alternate notation that can be convenient because, well, I'll show you how it can be more convenient. So we have alternate notation that for the line integral over the curve C of my vector field F, I could write this. This is a definition, right? In fact, the definition is from right to left, so the thing I'm writing on the right is the thing in symbols. Okay, so this is integral over C of m dx plus n dy plus p dz. Okay, why did we pick this notation? Well, if we're being Leibniz for a second, right, we're pretending that these dz dt's, dy dt's, dx dt's are honest to God quotients. They're like canceling out with the dt here, right? So what we have left is dx, dy, dz. What we mean, of course, is that this is dx dt, where x is the x, slot function of the parameterization. dy and dz are similar, right? Okay, and so that's what is meant when you see this expression. It is meant exactly this line integral, where I've used this notation mn and p for the components of the vector field. Okay, so let's do an example of why this might be useful sometimes, right, depending on the context. So here's the example. So let C be the curve. This is the twisted cubic we've talked about before. So here's the parameterization of C. It's ti plus t squared j plus t cubed k, and t lives in 0 to 1. Then evaluate the line integral over C of xy dx plus 3zy, or sorry, 3zx dy minus 5x squared yz dz. Now, why would writing using this notation be maybe preferable to the way we used to do it? Well, the way that we would have done this before, we would say evaluate this, right? We would say evaluate this where the vector field f is given by blah, right? So it would actually take us longer because we'd have to say evaluate the integral over c of f dot dr where f is equal to exactly this vector field written out in component form. So that's why we call this an abbreviated form, even if technically this is, not technically, this is definitely longer than writing the integral over c of f dot dr, but that's why it's abbreviated. It abbreviates what we have to do after. Okay. But also this provides a nice kind of like mental image of what it is you're doing when you compute a line integral, right? And so the way that I can think about this is I have this parameterization here. So this parameterization tells me that x of t, using my usual notation, is t, and y of t is t squared, and z of t is t cubed. And so then individually, if I think of dx, dy, and dz as being the dx dt, dy dt, and dz dt that I computed before, I can compute those things here. So I can compute dx dt. Well, that is just 1, right? So dx dt is 1. Dy dt is 2t. And dz dt is 3t squared. Okay. So then using this notation to my advantage here, I can say, well, this line integral is just the integral from 0 to 1 of, now I can just write all of these things out in the way that they're suggested by this notation, right? So this is t, right? So this is t times t squared. So that's x times y, t times t squared times dx, which is 1, right, plus 3z, which is t cubed, x, which is t, times dy, which I'm thinking of as dy dt, so that's 2t, plus, minus 5 times x squared, so that's t squared, times y, which is t squared, times z, which is t cubed, times dz dt, which is 3t squared. Right? Okay, and there's a dt there here. I'll write it. Okay. So then simplifying this a little bit, this is the integral from 0 to 1 of t times t squared, that's t cubed, plus 3 times 2 is 6 times t cubed times t, so that's t to the fifth, right? So this is plus 6t to the fifth minus 5 times 3 is 15. So t squared times t cubed times t squared, so that's t to the ninth, right? dt. Okay. So we can compute this without too much effort here. So just term by term, integral of t cubed is 1/4 t to the fourth. Integral of 6t to the fifth is just t to the sixth. The integral of minus 15 t to the ninth is minus 15 over 10, or minus 3/2 t to the 10. Okay, and all that is evaluated from 0 to 1. Plugging in 0, every term has t in it, so I get 0. So I just evaluate this thing at 1. What do I get? I get 1/4 plus 1 minus 3/2. So this is minus 1/4. Right? Okay. So visually, and for the purposes of organizing these line integrals, this notation can be kind of useful. Okay, for that reason. Okay. So, if there's no questions about that, I wanted to address one more conceptual thing that I think I've already mentioned before, but I just wanted to mention it again because unlike in previous sections when I mentioned some conceptual things, but typically when it comes to actually asking you to compute something like, for instance, the length of a piecewise curve that's really nasty and has like 5 pieces or something, you're going to be like, well, like that's not going to come out. It's not going to be a fair exercise or test question or something like that. But when it comes to these vector field or these line integral questions, I should say, it's very much a fair question. But the reason for that will come later. So I wanted to talk about line integrals over piecewise curves. So over piecewise smooth curves. So the idea is I have some curve in space maybe, but it looks like this. Right. Okay, so here's my curve C, and it's too much of a gap there. Let's fill that. Makes it look like it goes into like some other dimension or something. So here is my curve C. And of course, I view this curve as a bunch of curves kind of slammed together, right? Or we'll say concatenated together. So this is like, there's the first smooth piece, here's the second, here's the third, and here's my last smooth piece. And so how would I compute the line integral over my curve C of some vector field f? Well, as I mentioned previously, this is done piecewise. It's done over the pieces. So this would then become a sum of 4 of these things. Okay, and so doing it over pieces is bad if you can at all avoid it, because you have turned this problem that technically maybe you thought was a single line integral into 4 line integrals. Okay. So maybe you think, oh, well, like it's kind of annoying, but like it's doable. I could do it. It's for a problem, where you can actually brute force it like this, that's fine, but these could be really, really bad. So imagine, right? Imagine you have a curve, C. And the curve itself is not too nasty looking, right? Maybe the curve itself does a couple of loops like this, and then, I don't know, does something like that. Okay, so here's your curve C. All right, does something like that. Now you might look at that and you say, okay, well that's not too bad. It's not something that I can just look at and give a parameterization for that's nice. Okay, but let's say that the person that came up with this curve, since there are multiple parameterizations for a given curve, right? A given curve has many different parameterizations. So since there's many parameterizations that could be given, what if they give you a really, really nasty one? Right? So what if someone purposefully gives you a really, really nasty one, but they're the only person that actually knows, how to easily parameterize this thing. So you just kind of have to deal with whatever parameterization they give you, right? And so they give you something absolutely terrible for this curve. So let's see, what terrible parameterization for some curve can we have? Let's come up with something. Yeah, here's a good one. Let's consider the parameterization minus cosine of pi t to the fourth I, right, plus t to the 5/3 j plus t, actually let's make it t over t squared plus 1, we'll say, so we don't have domain issues here, k, and let t be in the interval -1 to 1. Okay. So where does this curve go? This is a curve. It has two endpoints. We could compute those endpoints really quickly by plugging in t here. So it turns out the endpoints are, if we plug in -1, that endpoint is, because of -1 minus, so this is 1 -1, because that's, I'd be raising -1 to the 5th. So this is, so 1 -1 -1/2 is the first one. And the second endpoint is 1 1 and 1/2, right? Yeah, that's right, 1 1 and 1/2. Okay. There we go. Okay, and so this is a curve between these 2 points. Here's the parameterization. But this is a pretty nasty parameterization, right? So imagine what you would be doing, right, when you compute the line integral f dot dr, right? The integral over the curve C of f dot dr. Well, let's just remind ourselves, right? What you would be doing is you would have this as your x of t, right? So here's your x of t. That gets plugged into your vector field, right? So this gets plugged into M. So even if your vector field is super nice, right, and not that complicated, right? For instance, like the vector field in our last example wasn't too bad. And here's the vector field. So even though this is not too complicated, I'd be plugging this in. Yeah, let's just even use this as our example here, right? So I would be plugging, so if I'm looking at this as our vector field from the previous example, I'd be plugging in this x of t in here, multiplying by y of t, that would be t to the 5/3, okay, times dx dt. Now I have to compute the derivative of this thing, right, and multiply by x and y, right, and then I add to that 3 times z, which is t over t squared plus 1, times x, which is this minus cosine of pi times t to the 4th, okay, times dy, which is the derivative of this thing, okay, minus 5 times this thing squared times t to the 5/3 times t over t squared plus 1 times dz dt, which is the derivative of this thing, right? Oh, I'm off the page when I'm pointing to my vector field here. Okay. So anyway, so you are plugging each of these things in for x, y, and z. This would get really nasty even for a vector field that's not too bad, right? And then on top of it, after you plug in all of that stuff, right, algebraically, then you have to integrate that horrifically awful thing, right, that shows up in the integrand, right? And the thing that you should remember is that there's no guarantee that you can easily integrate something, right? Like even something that's not that bad, right? So here's a little aside. If you have an integral of something like, x to the 7 minus x to the 5th plus 2, right, dx, can you integrate that thing? No, right? So, and you would potentially, with this kind of computation, end up with things much, much worse than something like this, right? All it takes is like one thing, right? One exponent is not the right thing, and the integral is like undoable, right, analytically. So, so in general, line integrals are nasty. So line integrals are very nasty. And a reason we might say that they're nastier, even though they end up resulting in just a normal integral, the reason that they tend to be nasty is that basically what you've seen, the examples that I've worked out, if we don't do something like that, if we don't make the vector field work out just right, or make it be like particularly simple, these things are very hard to compute in general. They're extremely tedious to compute. All right. So line integrals are nasty, right? So question, how do we best deal with the fact that line integrals are nasty? And the answer is that we have a couple of theorems to help. So we have a few theorems to help. Okay. Now these theorems require certain setups that are not always going to be true. So there is no general process that is going to fix your line integral problem. Sometimes you have a nasty line integral and you just have to compute it and there's no getting around it. Okay, but we are going to have a few theorems that help us compute line integrals in different ways. Okay. Okay. And so, the first one has a name that sounds very familiar, and it has that name because it it relies on the theorem that you already know that has that name, which is the fundamental theorem of line integrals. So this is our first big named theorem that says something about this. Now, before I state this, I'm going to give a little mini rant that I will give in multiple pieces for the rest of the semester. So, as I've mentioned before, right, if you follow the analogy between this course and Calc 1, this course is, in like very close correspondence to Calc 1. So Chapter 11 and 12 is just getting us set up. Chapter 13 is derivatives, right? So Chapter 13 is derivatives. Chapter 14 is integrals, right? And then, if you go to Calc 1 and how you did derivatives and integrals, once you got to the point where you had defined the definite integral and then you were ready to link up this integral with the notion of an antiderivative, you had two theorems. Technically, they were kind of combined, usually, or they were numbered. And those were called the fundamental theorems of calculus. They were the things that told you, right, that these quantities that you were computing, derivatives and integrals, were inverse operations to each other, right? That's basically what they were telling you. So what we are wanting to do is do that same kind of thing, but we're going to do it, for all these Calc 3 quantities. The main problem here is that, as we've already seen, in higher dimensional things, there's not a notion of the derivative, right? There's not one operation. If we're talking about vector fields, right, we had two different operations that kind of, for us, served as a way of taking a derivative of a vector field, right? One was a divergence, one was a curl, which we haven't really talked about since. But those are coming up. Those are coming back. And so we don't have one unified way of talking about the derivative. We also don't really have one unified way of talking about the integral. Okay, so we're going to get around that by just having a bunch of different theorems, all of which are really a special case of some one big mega theorem, which is a very deep, very nice but very complicated theorem called Stokes' theorem. Okay, we are going to see a version of a theorem called Stokes' theorem, which is going to be a special case of the actual mega Stokes' theorem. And all of these named theorems that we're going to talk about are all special cases of, we'll call it mega Stokes' theorem. And I'll go through that when we get to the very last bit. Okay, so what's the fundamental theorem of line integrals? So I'm going to give the statement, then I'm going to interpret it. Right, so the statement of the fundamental theorem of line integrals is the following. So let C be an oriented curve. So that is a curve together with an orientation. We know that if we're given the smooth parameterization for C, then we already have the orientation included implicitly, right? So let C be an oriented curve with initial point x naught, y naught, z naught, and terminal point x1, y1, z1. Okay, let f of x, y, z be a function of three variables that is differentiable at every point on C. It is differentiable on C, and assume that the gradient of f is continuous on C. This is all you need. Okay, then the integral, that is the line integral of the gradient of f, has a special form. So before I write what this form is, I should say it is only natural, right? And I've mentioned this several times since we started chapter 15, that you're curious when it comes to the gradient as an example of a vector field, since it's our first example of a vector field, right? The gradient of a function of three variables is our first example of a vector field in space. So it's only natural that when you have any quantity that does something to vector fields, that you ask, what does it do to the gradient, right? We did that for the divergence, for instance, right? We did that for the divergence. The divergence of the gradient was this special thing called the Laplacian, right? The curl of the gradient, right, also had a special form. So go back and see what that was. This idea, right, is not new. Now we're just applying it to line integrals, right? So we defined line integrals. We worked out what line integrals were in the previous section. Now I want to basically do line integral of the gradient of some function. What is this? Well, it is f of terminal minus f of initial. And then that's it. Okay. So, there's a lot to say here, right? A lot to unpack from this statement. One, you see how this is a partial answer to this question of how you deal with the fact that line integrals are nasty. Because what does this say, right? Among other things, right? This says that line integrals are really easy to compute if the thing you're integrating is the gradient of some function, right? What is this telling you, right? What is this related to? Remember at the end of the first section of chapter 15 when we were asking the question, when was a vector field conservative and how did we know, right? And so taking the curl of the vector field gave us a hint, right? We knew that if f was a conservative vector field, it had to have curl that's zero vector. Right, so the curl of the vector field had to be the zero vector. Well, if the curl is zero vector and it's conservative, that means it's the gradient of some function. But how did we actually find what function it was the gradient of? This was this process we went through, right, to go backwards, right? And we could only do this if our vector field is actually conservative. You'll find that it's impossible to do if it's not. Okay, and so notes. Let's see what is said by the fundamental theorem of line integrals, so FTLI. So it says a lot. Okay, so one, if f is a vector field that is conservative, i.e., f is the gradient of little f for some function little f, then it is very easy to compute the line integral. Why? Well, in that case, the line integral of f, since f comes from the gradient, well, that just means that this is the line integral of the gradient of f, or of little f, which is just point minus point, right? It's just at little f of terminal minus little f of initial. Okay. So if you have this little f in front of you, clearly this is way easier to do than actually computing the line integral, right? If you do it the long way. Okay. A good way to check if you wanted to practice line integrals, you could come up with, a function little f, take its gradient, that gives you a vector field, and then come up with, some whatever nasty parameterization you want for some curve, or just come up with a decently simple parameterization for the curve. Do the line integral the old way, and then do it using the fundamental theorem of line integrals, and check your answer. Right. So this is a nice way of being able to do that. Okay. So what else is said by this? So a lot of conceptual stuff is going on here. What about if C is a loop? So if C is a loop and F is conservative, right, I'm not always going to say that. Sometimes I'm just going to say F is, the gradient of some little f. Okay. Then what do I know? My line integral of f over this loop C, right? So here's my loop C. What does that mean? It means the terminal and initial point are the same, right? This is the integral over c of gradient of little f. So this is little f terminal minus little f initial, but these are the same. Right? So that's interesting, right? This means that if I have a conservative vector field and I take the line integral of that conservative vector field over any loop, any closed smooth path like this, what I get is 0. Okay. So interpreting this as work tells me what? This is telling me that the work done by a conservative continuous force on an object that traverses a closed piecewise smooth curve is 0. Okay, so this is the reason for this word that we use, conservative, because it has to do with statements on conservation of energy, for instance. Okay. All right. So these conservation laws in physics follow from these mathematical facts concerning these conservative vector fields, or what we're calling now conservative vector fields. Okay. What else do we notice? Well, if f is conservative, then its line integral is independent of path. What does that mean? Well, imagine I have beginning point and terminal point, right? Big A and big B. Okay. If I have a bunch of different curves here, okay, okay, I'll do one more. All right, there's a bunch of different curves connecting those 2 points. I'll label the curves. We'll say C1, C2. We'll make C3 the curvy thing. C4 will be the line connecting A and B, or that line segment. C5 and C6. Okay. Well, if f is conservative, right, if the vector field f is equal to the gradient of little f, then since in doing the line integral of such a vector field along any curve is just the same as integrating the gradient along any of those curves. This is always little f of terminal minus little f of initial. Or in this case, B and A here, right? And so it doesn't matter what C is, because the endpoints are the same. The line integral along each of these C's is the same. So the line integral of such an f over C1 is equal to the line integral over C2 is equal to the line integral over C3, and so on. Okay. All these are equal. And so we have this terminology, path independence, or we say that the vector field is independent of, or the line integral is independent of path of such a vector field because it doesn't actually matter what curve you integrate over if you're not changing the thing that you're integrating here. Integrating over all these curves, so long as they have the same initial and terminal points, you're going to get the same thing. Okay, so that's clearly a special thing that's not always going to occur for general vector fields and curves. But for vector fields that come from the gradient of some function, this is true. So now we see why it is important to be able to find little f such that the gradient of little f is equal to big F for a given conservative vector field. Big F. Because this will allow us to use fundamental theorem of line integrals to quickly knock this out. Now I have some bad news. The bad news is that for most of the rest of the semester, we're not going to be able to use the fundamental theorem of line integrals. Okay, applying it to conservative vector fields is too nice, right? It's too easy. Okay, so it's too easy to settle these questions. So mostly what we're going to be concerned with is when we can't do this. Okay, but nevertheless, this is really, really nice. And so if you're in the case of having a conservative vector field, you can immediately use this to compute a line integral and makes your life very, very easy. So at the beginning of next lecture, I will kind of tidy up the list of facts that follow immediately from fundamental theorem of line integrals. And after that, I think what I will do is pretty much go immediately into discussion of Green's theorem. I might do like one or two examples of doing using the fundamental theorem of line integrals. Then I'll move on directly to Green's theorem, and then we're going to go from there to discussing surface integrals, which a lot of that background has already been discussed, so we'll be able to get into that pretty quickly. And then on to the last two big named theorems. So the end is fast approaching. So anyway, I will see you all next time.